How are you, doctor?
Yes, thank you, sir. So before I start, I would like to thank you, Dr. Roberto J. Marin, for organizing this 2024 Landslide Scientific Assessment Conference. And I would also like to thank you all the presenters and participants who has joined in this event. So myself, Suvam Das, I am a research scholar of ACSIR at CSIR Central Building Research Institute, Roorkee. And thank you for giving me the opportunity to talk on a topic titled Stability and Hazard Assessment of the Progressive Zero Landslide in the Kalimpong region of Darjeeling, Himalaya. So as you all know, landslides are quite frequent around the world, and every year this recurrent hazard cause extensive damage in terms of loss of life and property. So if you see this global fatal landslide database compiled by Frode and Professor Petle, it is clearly indicated that almost all countries around the world have or has experienced fatal landslides. And these fatal landslides caused around 18,000 deaths, and in which India and China are the most affected one, in which India solely shares 18% fatalities in the global database. In India, particularly the Himalayan terrain is more susceptible for landslides. If you see this figure, it shows the normalized kernel density of past landslides occurred in Himalaya. So it is shown that the Western Himalaya and the Eastern Himalayan parts are the major hotspot zone of landslides. So for today's presentation, I choose a landslide located in Darjeeling, Himalaya, and I will present a detailed investigation of this landslide. So in Darjeeling, Himalaya, landslides are quite frequent. So this table shows the past landslide events that occurred in Darjeeling, Himalaya. So if you see this table, it is clear that the rainfall is one of the major landslide trigger in this part of Himalaya, followed by some occasional earthquakes. So in which this 1968 event is the most devastating one. So this figure shows the post-event figures of 1968 event. You can see that the thousands of landslides are triggered in this Darjeeling, Himalaya. So if you also see this district survey report, it is clear that most of the area is come under very high to high susceptible zone. So despite the landslides are quite frequent in Himalaya, there are certain challenges that often limits us their detailed investigation. So these challenges include the sudden occurrence of landslides, followed by, if you compare the frequency of landslides with other natural hazards, let's say flood and earthquakes, it is evident that the high frequency of landslides stands as a practical problem. Other than this, if you compare the return period of landslides, it may be range from annual to seasonal, whereas in case of flood and earthquake, it may be 10 years to 500 years. Next challenge is the size or magnitude of landslide. So in case of landslide, it can be range from a single rockfall to the collapse of the entire hill slope. So whatever modeling one have to done, it should be addressed these both size categories. Other than this, these two figures clearly indicate that the risks of landslide particularly depends on its location rather than its size. Okay, the next is the material involved in the landslide process. So basically, this is the subsurface geology map of this Kalimpong, Darjeeling, Himalaya. So this basically shows that this is the location of the zero landslide, where the subsurface geology is mainly comprises of paro gneiss type of rock. Okay. So, and if you see, this landslide is closely associated with this thrust zone, and geologically such areas are described as weak zone, and when they are subjected to triggering factors, landslides are generally occurred. So if you see the rainfall data that was collected from a local station nearby this landslide, it is clearly indicated that the 80 to 85% of annual rainfall occurred during the monsoon period. So such high intensity rainfall frequently triggered landslides in this Himalaya, in this part of Himalaya. So this slide shows the geomorphological characteristics of the landslide site, particularly the figure number A and B. So figure A shows the elevation map of this area, and this black mark shows the landslide polygon mark. Okay. So from the elevation map, it is clear that there is a high elevation contrast is there in the landslide site. Similarly, if you see the figure number B, the slope of this area is highly steep, and such geomorphological configuration often favors landslide. Other than this, if you see the figure number C, it is shows the temporal traces of landslide. So it is started in 2014, and the satellite data sets we have collected up to 2022, and within this date the traces of landslides are marked here. So from these traces, it is clearly evident that a retrogressive progression is there, and this landslide is threatening the upslope settlements and roads. So this figure particularly shows this field photograph of this landslide. So you can see that in the crown section, a school building is there, followed by a Nimbong village is there, and other downslope roads are there. And all these risk elements are highly threatened by this landslide. And this figure shows the field photographs. At the crown section, you can see that the tension cracks are there. If you can also see that the earlier roads are damaged, and the exposed rock structures are in very poor condition. And and this analysis shows the NDVI based analysis. So by interviewing locals, I know that this landslide was first occurred in 16 July 2014. So this same thing can also be observed from this NDVI result. If you see that prior to the failure, these values are in higher side, and once this failure occurred, this high variation can be observed. Okay. So following this, I also did a INSAR based analysis for this landslide, and for this I used SBUS INSAR method. And for this SBUS INSAR analysis, I used Hype3 and MinPy processing platforms developed by Injunator 2019. So this figure shows the methodological flowchart used for SBUS INSAR analysis. It started with downloading Sentinel-1 SLC images to the up to the velocity estimation. And this figure shows the average spatial coherence captured by Sentinel-1 SLC images. So you can see that the spatial coherence values are typically low for this area. So this may be due to the presence of dense vegetation in this area, which often occurred due to the diffuse scattering of microwave waves. And this figure shows the interferogram network for Sentinel-1 ascending and descending orbit directions. And this shows the SBUS INSAR derive line of sight velocity estimation for the ascending and descending orbit direction. So these results actually come in 40 meter by 40 meter pixel format, but for representation purpose, I used this point format. So it is clearly evident that the movement is there in this landslide. Uh, and if you see at the crown section, near the crown section of this landslide, high movement can be observed. And this slide shows the time series distribution, time series line of sight velocity estimation along the ascending and descending orbit directions. So for the ascending orbit, I obtained a maximum velocity of negative minus 8.21 semi per year, and for the descending orbit, the velocity was around negative 11.5 semi per year. So following the SBUS INSAR analysis, I also estimate the velocity and volume of this zero landslide. So for velocity estimation, I used a empirical method, and for to show this, I use this figure for example purpose. This is a famous Kaliasur landslide in Uttarakhand, Himalaya. So let's assume I have this slope, and you can easily determine the height, length, and the energy line of this slope, either using digital elevation model or field measurement. And if you put a block here, Due to the action of gravity, this block will slide down. So Seidegger used this concept and proposed this equation to estimate the landslide velocity along the runout path. So by applying this equation, I obtained this velocity profile for the zero landslide, which indicates a maximum velocity of 21 meter per second. But I think this velocity is overestimated due to non-consideration of bed frictional resistance. Yet, but this can give a first-hand information. Other than this, I also used this ellipsoidal method proposed by Kruger 1976 to estimate the landslide volume. The operations are in the form of fifth order of magnitude. Okay, following this, I did the stability assessment. So for stability assessment, I used this finite element modeling. So this shows the configured slope profile where finite element this noded triangular finite element mesh is used and appropriate boundary conditions are applied. And to define the material properties, we field study and also did some lab investigation, and based on in based on this we get a critical factor of safety value of 1.07 for dry condition and a unstable value of 0.78 for wet condition. To generate the wet condition, RU based pore water pressure coefficient, which clearly indicates during the rainfall exposure. So based on this attempt, our key findings are that the crown section of this landslide have a high chance of failure in near future. For designing and implementation of mitigation is required to further loss. So based on this study, there are some limitations are there which can be also incorporated as aim for future research. This include the present analysis mainly limited. So let's assume we have did direction test and get C5 value, and we use it for our numerical. So Luca shows some CPQ's values you can see in his presentation, the earlier presentation. So such uncertainties can be easily incorporated using this probabilistic analysis. Other than this, we can also consider these uncertainties in terms of spatial variability, that these properties can be vary both horizontally and vertically. And lastly, the most important thing is the designing the stability measures and perform the coupled sequence stability analysis to get the more realistic results. And these are the references that I used during this presentation. And these are the two publications related to this presentation. And thank you.